No.
Sir. The whole bottom of the device. Also, they're definitely spilling it. I hate it here, Marty.
What are you doing?
So can people hear me on the other end? All right, can someone let me know if they can hear me?
Yep, we can hear you.
All right, thanks.
Yeah.
Okay, so we should probably begin. So the first thing is I actually was able to grade all the midterms this past weekend. So what I'll do is I will send you a message on how to pick up your midterm. So most likely what will happen is I'll bring them to class for about a week. So if you want to just stop by during the class period, it doesn't matter whether it's your assigned class period or not. You can still just come by and pick it up. If you want to, you have to take off. That's okay too. So I'll actually give you some instructions on how to do that. Okay. Overall, I was very pleased with how people did. So keep up the hard work. All right, so today what we're going to do is we're going to look at decompositions. We're going to look at decompositions of matrices. And in the process of decomposing these matrices in terms of a lower triangular matrix, a diagonal matrix, and then an upper triangular matrix, we'll see that we can just use the Gaussian elimination procedure to do this. All right, so this section is called triangular factors. Okay. And so the idea is I'm going to take A, and this is going to be an n by n matrix. Okay. And in the process of Gaussian elimination, I'll be able to factor A in terms of L times U, where L is a lower triangular matrix. And U is in upper sort of row echelon form. So I'll be able to actually do this as long as there are no row exchanges. So as long as okay. And in fact, what we can do is we can do a little bit better. We'll be able to factor A in terms of LDU, where D is, let me call this U prime. Let me call this one U prime, actually. I'm just gonna, oops. Let me try to erase it first. That's not working. Okay, that looks a little bit better. So, yeah, so this should be a U prime here. Okay. And then it's LDU, D is diagonal matrix. Again, U is upper sort of triangle. It's not necessarily triangle, it's sort of an upper row echelon form. Okay, so I'll be more specific about this later on. Okay. All right, so let's start with an example. And then I'll show you how to do this. Okay, so why don't we start off with a system of equations. So let's start off with 2x plus y plus z equals 1. 4x plus y is equal to minus 2. And minus 2x plus 2y plus z equals 7. All right, so this is a 3x3 system of equations. Now, as we know, we can sort of write this as ax equals b. So we have the matrix A here, and here's the x vector, and then the b vector is over here. So let's fill these things in. So this is 2, 1, 1, 4, 1, 0, minus 2, 2, 1. And b is 1, minus 2, 7. Okay, so this is A here, and this is the vector B. Okay, so as we know, the system of equations is equivalent to looking at AX equals B. Okay, so in order to solve the system of equations, we use Gaussian elimination. So let's just do that. So this is 2, 1, 1, 4, 1, 0, minus 2, 2, 1, 1, minus 2, 7. Right? Okay, so we're just going to proceed as we normally do. We're going to look at a pivot. We're going to knock out some things right underneath the pivot. So the first thing we're going to do is we're going to multiply the first row by minus 2. We're going to add it to the second row and put it in the second row. So this is 2, 1, 1, 1. And what do we get? We get 0. And then we get minus 1, minus 2, and then a minus 4. Okay? And then we keep this one the same. Okay? All right. Now, this system of equations is equivalent to the first one. So, you know, if we set this one to be equal to A tilde, and this one to be B tilde, so this system of equations is A tilde x is equal to B tilde. All right? And what does the matrix A look like? The matrix A here, tilde, looks like 2, 1, 1. I'm writing this out again, so that's just to make it more clear. Okay, and the B here, tilde, equals 1 minus 4, 7. Okay. Now, let me put up the A again. Okay. So I'm going to do a little comparison shopping here. So here's the A, and let me rewrite the A up here. So it's 2, 1, 1, 4, 1, 0, minus 2, 2, and 1. So here's a question. How does A tilde, how does it differ from A? Okay, so let's do some comparison. So the first row of A is the same as A tilde. The third row of A is the same as A tilde. Right? So the second row is different. Right? So can anyone think of like how we get from A to A tilde by matrix multiplication? The question I'm going to pose. So another question is, can we obtain A tilde from A by some matrix multiplication? Well, you know, one thing is if we do multiply, let's say A on the left, then we have to keep the first row and the first column. So I want to consider the following matrix. E2, 1. And this is going to be the matrix 1, 0, 0. And then I'm going to keep the second. Okay, so think about E21 here and then multiplying on the left of A by E21. Okay, so I'm going to pick out the first row by doing this. I'm going to pick out the third row by doing this too. Now, I want to put -2 times the first row. So what I want to do, I'm going to take -2 times row 1 plus row 2, and I want to insert it into row 2. Okay? So when you matrix multiply, if I put a -2 here, that part's going to multiply the first row by -2, and then I'm going to add it to the second row, and then it's going to actually put it in the second row. Okay? So you can see that if I take E21A, then I get A tilde. Does everyone see that? Yeah, this matrix multiplying that. And moreover, if I take E21 on B, I get B tilde. Okay, so this process of Gaussian elimination is really multiplying matrices on the left. Okay, by these what are called elementary matrices. Okay, so let me present the idea more precisely. So performing -2 times row 1 plus row 2 being inserted into row 2 is equivalent to multiplying AX equals B on the left by the matrix E2. Okay. Any questions on this? Questions? Okay.
Yeah, I have a question. Sorry.
Go ahead.
Why do you have a sub of 2, 1?
Oh, that's a good question. Second row, first column. That's where we put what's called a multiply. Okay, so this is in the 2, 1 position.
Okay,
Okay, good question.
thank you.
Other questions? Oh, just matrix multiply. It means do this. I'm just multiplying E21 on the left of this equation, AX equals B. Okay. I don't know. Let me be a little bit more precise about that. So if I take AX equals B, then all I do is I take E21 AX equals E21 B, and then this is just going to be E tilde X. That's exactly right. It's actually in my notes. All right, let's continue on. Okay, so I don't know, maybe I should. Okay, I don't have the space to kind of go up and down here. So let me rewrite things so that we can see where we were at before. Okay, so back to the example. Okay. All right, so let me just kind of go back and put the matrix in that we were at. 2, 1, 1, 1, 0, -1, -2, -4, and -2, 2, 1, and a 7. Okay. Great. Okay, so what do we do? Well, we're going to multiply row 1. So 1 times row 1 plus row 3, and we're going to insert it inside of row 3. Okay? All right. So just like before, what we'll do is that we can just multiply on the left by E31. And that's the matrix 1, 1, 1. And then we put, what do you think we put in the 3, 1 spot? What do you think goes there?
1.
A 1. Okay? So take this matrix and apply it to this matrix right here. And you see it just keeps the first row the same. It keeps the second row the same when you multiply on the left. And it just takes the 1 times the first row plus the third row, and then it inserts it in the third row. Okay? So what I get is I get E21 A tilde is equal to A tilde tilde. Okay? And so let's do that. Okay, so let's see, we get 2, 1, 1 here. The 1 stays the same. Second row stays the same. Third row becomes 0, 3, 2, and an 8. Okay? And so this is A tilde tilde. This is B tilde tilde. And then I have an E31, so that's 3 not a 2. Okay? Times B tilde is equal to B double. That's tilde just means the next step. Second step. Okay, we're almost there. Any questions so far? So you can kind of see what we're doing, right? And then one more step. So what we want to do is we're going to multiply this by 3. So we take 3 times row 2 plus row 3, and we're going to insert it into row 3. Okay? And so what are we going to do? We're going to take E. So what do you think the subscript's going to be? So I'm going to put the E over here without the subscript, and we'll put it in a second. So what do we want to do? We want to keep the first row the same, the second row the same, and then we want to take row 3 times row 2 plus row 3. So what do you think the last row of this matrix should be? What should it look like? Anyone?
0, 3, 1.
Good. Okay. Now this is in the third row, second position, right? So this should be E32. Okay, so E32 times A double twiddle is equal to A with 3 twiddles. And E32 with B with 2 twiddles is equal to B with 3 twiddles. Okay. So let's do that. And then we'll collect all the data here. So this is 2, 1, 1, 1, 0, -1, -2, -4, 0, 0. Minus 3 times minus 2 is minus 6, plus 2 is minus 4. And finally, I get a minus 12 plus 8, that's minus 4 also. All right. Okay. And again, this is U. It's called U prime, which is A with the triple twiddle, and this is the B with the triple twiddle. Okay, any questions so far? Okay, so now how did we get U prime? So we obtained this U prime, which is this nice sort of echelon form where the pivots may not be just ones or zeros, but could be something else, by doing the following. So we took A, and then we first applied E21, and then we applied E31, and then we applied E32, and that's U prime. Okay? And I don't know, for the sake, let me call that B prime. And so how did we get B prime? Well, we took B and we just did the same thing. Okay? All right, so that's how we actually get this. We reduce.
Professor, should the middle E for B prime, should that be E31?
3-1, thank you. So AX equals B sort of reduces to, and we've done this to something like U prime X is equal to B prime. Okay? So the way that we're doing Gaussian elimination is we're just applying these elementary matrices on the left and to do row operations. Okay. So we should keep this in mind. Okay. All right. So now I promised that I want to decompose A in terms of L times U prime. Right? So what do we want to do? We want to actually take the E's over to the other side. So these are square matrices, and they turn out to be invertible. So E21 is invertible with inverse E21 inverse equals 1, 0, 0, minus 2, 1, 0, and 0, 0, 1. Okay, so I don't know. Let's just check really quick. 1, 0, 0, minus 2, 1, 0, 0, 0, 1. Okay, so this is E21 inverse. And then remember what E21 was, 1, 0, 0, 2, 1, 0, 0, 0, 1. Okay? All right, so if I take the dot product with all the columns, I'm just going to pick out the first row, right? Like that. And then the next one is I take the dot product of this with all the columns. So I get 0, 1, 0. And then the dot product of the first row of E21 inverse with the columns of E21 is 0, 0, 1. So lo and behold, okay. All right. So what I can do is I can take we call this 1 here. So I want to take equation 1, and I can multiply by the inverse of all these matrices on, and make them inverses on the right. So A will be, okay, so U prime, so I have to take the first inverse, it's E21 inverse, or E32 inverse, okay, E31 inverse, and then finally E21. Okay. All right, so that's good. And notice that this is lower triangle. The inverse is lower triangle. So whenever I take lower triangular matrices and I take the products of lower triangular matrices, it's also going to be lower triangle. So this will be here, lower triangle. Okay. All right. So on a set, this lower triangular matrix to be E21 inverse, E31 inverse, E32 inverse. And there's a nice way to actually get the inverse for the product of these matrices. So what you do is you just take the multipliers that you had, namely 2, 1, and, sorry, the multipliers were 2, right there. Okay, so the multipliers were -2, okay, in E21, and 1 in E31, and 3 in E32, okay? So what you do is you take the negatives of the multipliers, and then you put them in the appropriate position. So it's -2, so 2 is the multiplier there for E21, and then -1 and -2. So here you put, in here, you put the negatives of the multipliers. Okay, so once you actually know the multipliers, you just can shove them in the right spots with their negatives, and then that gives you L. Okay? All right, questions up until this point. So I have A equals L times U prime. Okay, so now I know how to get L, and I also know how to get U prime. Okay. All right, so here's the theorem. Okay, so let A be an n by n matrix. It doesn't need to be 3 by 3. And suppose no row exchanges are needed in the Gaussian elimination process to get it into just an upper triangular coin. So that A is going to be equal to L times U prime, where L is, let's see, an m by n, lower triangular matrix, and U prime is an m by n matrix in echelon form. not reduced echelon form, just echelon form. Okay, so this example illustrates how to do that. Okay, questions on this? Okay, so now there's actually a further refinement. On U prime. Okay. So let me take U prime again, our example. So what was U prime equal to? Okay, so let me so I have 2, 1, 1, 0, minus 1, minus 2, and 0, 0, minus 4. Okay. So what you can do now with U prime is you can factor further so that the 2, minus 1, and minus 4 become 1s. And the way you do that is you just divide the first row by 2 and divide the second row by minus 1 and divide the third row by minus 4. So that's the same thing as doing the following. So U prime is equal to what? So let's put the diagonal entries over here. But to compensate for these diagonal entries, I have to divide by 2. So this is 1, 1 half, 1 half, 0, 1, 2, 0, 0, 1. Okay, so this is a diagonal matrix, and this is a echelon form matrix, which is reduced. Namely, the pivots are either in the pivot spot you have just 1s. Okay, is that clear? All right, so now, okay, so this one is diagonal here. And this one is in this reduced echelon. Great. And so now, therefore, A is equal to LDU, where L is lower triangular. Okay. D is diagonal. Okay. And U is in reduced, I'll just say upper echelon form. Okay, so again, this is if no row exchanges are needed. Okay, so I don't know. Let me did we actually do this? Okay, so let me just kind of recap our example. So back to the example. So we started off with this matrix here. Let me get it for you. 2, 1, 1, 4, 1, 0, minus 2, 2, 1. All right, so that's the matrix A right there. And we factored it in terms of 3 matrices over here. So let me rewrite those 3 matrices. Okay. So remember, L was the product of the inverses of the lower triangular matrices, the elementary matrices. So I have 1, 1, 1, and then you have the negatives of the multipliers. So minus 2, minus 1, minus 3. Okay, so this is our L. And then the D we obtain by taking the pivots and putting them along the diagonals. Okay, so the pivot is going to be 2, minus 1, and minus 4, and that's our D over here. Okay? And then we had our reduced echelon form, which is a matrix like this, and 0, 1, and this was our D. Okay, any questions on this? So again, when you use Gaussian elimination, you actually know how to do this because you just keep track of the data when you do Gaussian elimination, and then you could find L, D, and U all the time. And this decomposition is unique. Okay, so here's the theorem, or fact, if you want to call it. The LDU decomposition is unique. That is, if A is equal to L1, D1, U1, and if it's equal to L2, getting back on the swing. Oops, maybe not. Okay. L2, D2, U2. Okay, so if you have LDU decompositions, possibly different ones for A, so then L1 has to be equal to L2, D1 has to be equal to D2, and U1 has to be equal to D2. Okay, let me pause for a second. Any questions on this? We'll do another example later on, probably at the beginning of the next class, just as a review.
We do these same operations for B as well.
Or you could do the same operations for B, exactly. And the advantage there is, you reduced your system down to a system that you can solve using like back substitution. Okay? Good. Okay. All right. Now, what about row exchanges? So let me talk a little bit about row exchanges. So what about row exchanges? Okay, so sometimes, in the process of Gaussian elimination, you want to switch rows so that you can sort of use the pivots in the right places. So let me give you an example. Okay, so what I'm going to do is I'm going to write a matrix over here which you need a row exchange. So 1, 0, 1, 3, 2, 6, 1, and 5, 1, 2. Okay? So what I'd like to do is I'd like to switch row 1 and row 2. So we want to switch row 1 and, of course, row 2. Okay? Now, we have to just use our imagination. And we want to keep row 3 the same. Right? So what I want to do, and maybe I'll use a little color now. Okay, so let's see. All right, we can use this color here. It's my favorite team won yesterday. Okay, so, all right, okay, so I want to put a matrix here, a green matrix. All right. Now we want to keep row 3 the same. So as we know, we can just do that by just doing 0, 0, 1. Okay. Now I want to interchange rows 1 and 2. So if I take the first row of the green matrix, I want to pick out row 2. So how do I do that? What entry should I put up into that green matrix in the first row? Pick out row 2.
0, 1, 0.
Very good. 0, 1, 0. And then I want to pick out and put in the second row of the resultant the first row of the black matrix. So what should I put in the second row of the green matrix?
1, 0, 0.
Good. 1, 0, 0. And this is called a permutation matrix. It's just the identity matrix where you've actually permuted a couple of the rows or a certain number of rows. So this thing is called a permutation matrix. Okay? All right, so let me go back to the normal color here. And now the resultant here, all you do is now you just take 2, 6, 1 here, 0, 1, 3, and 5, 1. Okay, so this is a permutation matrix, and we're going to call this permutation matrix P21. So you interchange rows 2 and 1. Okay. All right. And if you want to call P31, we can interchange rows 1 and 3. What do you think we do? We take 0, 0, 1, 1, 0, 0, 0, 1, 0. Okay, and then if you want to do rows 2 and 3, so we'll call 3, 2. So let's see, we keep the first one the same, 1, 0, 0, and then 0, 0, 1, 0, 1, 0. Okay, so these are other permutation matrices. Monday, right? Okay, let's try it again. Other permutation matrices. Okay. All right, so now we have these permutation matrices that allow us to switch rows. So what we can do to A, if it needs row exchanges, is just multiply it by a product of permutation matrices. So if we need row exchanges, then what we can do is we can multiply on the left of A by a permutation matrix. Permutation matrix, call it P. Okay, that does row exchanges. So we have P times A. And P times A now doesn't need any row exchanges because it's in the right position. So the rows are in the right position, so you can use Gaussian elimination. So then, since we know P times A doesn't need any row exchanges, then it has an LDU decomposition. So then P times A is equal to L du. Okay, so that's the theorem. That with row exchanges, we just pre-multiply by permutation matrix, and that has an LDU decomposition. So again, L is lower triangular, D is diagonal, and U is upper triangular. Sorry, that's not right. It's in row echelon form. But reduced, this is reduced the upper echelon form. Okay, good. All right, so no matter what, once we actually can do the row exchanges, then everything is sort of good to go. Okay, any questions on this procedure at all? Yes? No. Okay. All right, so next time what we'll do is we'll go back and we'll practice on an example. So next time we are going to practice another example of this. Okay, so that's the first thing we're going to actually do. So we'll just try to hone our skills a little bit by doing another example just to make sure we understand the concepts. And then after that, we're going to go into talking about, I believe, subspaces of Rn. So we'll discuss certain subspaces defined by the span of certain vectors, and then like the row space and the column space and the null space, and then we'll make connections with these subspaces. I have to actually define what the subspace is. Okay, great. This is all I have for today. Any questions?
So you said you were going to send a message about our exams, like when we could pick them up?
Yeah, so what will happen is I will send you over email sort of the distribution of the scores, just generally speaking. And then I will let you know, I mean, basically, it'll be something like you can pick up your exam starting from Wednesday till the following Wednesday. I'll bring them in. After that point, if you haven't picked up your exam, just send me an email. We'll schedule a time for you to pick up your exam. So it would be better if you picked it up within the next week or so. Okay?
Thank you.
Good. Other questions?
I have a quick question about maybe the application of this Gaussian elimination being just a matrix multiplication. So when we multiply all these matrices out, it almost seems very systematic, right? So is this how a computer or a calculator does Gaussian elimination?
Yeah, so it turns out that Gaussian elimination is an algorithm, and it doesn't necessarily need to do matrix multiplication, but you can actually think of it that way. And so at every step, I mean, it is a process where you're taking either a combination of certain rows and then replacing that row by something else. So yes, that's what computers actually do in terms of solving systems of equations. And they're very fast at doing this kind of thing.
Right, because it's very elementary.
Yes. And I think you can actually do this in polynomial time. Like I think it's something on the order of n cubed.
Okay, thank you.
Okay.
So I have a question. The homework for this week, is it 2.2 and 2.3?
Yes,
Okay.
I believe, yes.
Okay. Thank you.
Almost 5, I believe.
Okay.
Yeah. Great. Okay, good. So we will see you on Wednesday.
Thank you.
Welcome.